Good evening, everyone. In the last class, we discussed about the vector form of Coulomb's law. And the vector form of Coulomb's law was like if we have two charges placed in a Cartesian coordinate system, then how do we calculate the force acting on the two charges in a vector form? The vector form of Coulomb's law not only gives us about the magnitude of the force acting on the two charges, but also the direction of the force on the two charges. Suppose that we have two charges placed. This is our Cartesian system. That's our y-x plane. And suppose that we have charge 1, q1, and the charge q2 here. And the position vector of the two charges is, the position vector of charge 1 is r1, and the position vector of charge 2 is r2. And the displacement vector between the q1 and the q2 charges is represented by this r vector. Then the force on charge 1 because of the presence of the charge 2 is given by 1 upon 4 pi epsilon naught q1 q2 r1 vector minus r2 vector upon modulus of r1 vector minus r2 vector cube. And similarly, we also found that the force on charge 2 because of the charge 1 is given by the q1 q2 upon 4 pi epsilon naught r2 vector minus r1 vector upon the magnitude of r2 minus r1 vector whole cube. And this force between the two charges in vector form is provided the two charges are placed in vacuum. The same two charges are placed in some medium of dielectric constant, let's suppose epsilon r, medium of dielectric constant epsilon r, then the force between the two charges will decrease because of the presence of some dielectric medium, and the force will be modified like F1 F2, that the force on charge 1 because of charge 2 it will be q1 q2 upon 4 pi epsilon r into epsilon r, and rest of the things will be same. And similarly, and in the same manner, the force on charge 2 will be given by F21 in a dielectric medium, that's q1 q2 upon 4 pi epsilon naught into epsilon r, r2 vector minus r1 vector upon mod of r2 vector minus r1 vector whole cube. So that's how we calculate the force between the two charges, provided the two charges are placed in a vacuum or in a medium. If the charges are placed in a medium, the force between the two charges will reduce by a factor of 1 upon epsilon naught. 1 upon epsilon r, where epsilon r is the dielectric constant of a medium or relative permittivity. Epsilon r is nothing, it's equal to epsilon upon epsilon naught, where epsilon is the permittivity of medium and epsilon naught is the permittivity of free space. Now let's discuss if there is a presence of more than two charges in a space or in some medium, then how the forces between the forces between the n number of charges varies. One important point is that the Coulomb's force does not change upon the presence of any other charge in a medium. Or you can say Coulomb's law does not change upon the presence of any other charge in a medium. If we have n number of point charges placed in a medium, like suppose this is Q1 here, and this is Q2 here, this is Q3 here, and this is Q4 here. And suppose the force on Q1 because of the Q2 is F given by the F2 vector, and the force on Q1 because of Q3 is given by F3 vector, and the force on Q1 because of the Q4 is given by F4. So any presence of any other charge, suppose the presence in front of charge Q1, there are three more charges, that's Q2, Q3, and Q4. The force that Q2 applies on Q1 does not depend upon the charge Q3 or Q4. Q1 and Q2 will interact in the same manner as if the two charges were interacting with each other. But the net force, on the charge Q1 because of Q2, Q3, and Q4, it will be given by the vector sum of all the charges, vector sum of all the forces because of the individual charges. That's what we call as superposition principle. If n number of charges are placed in front of a point charge, then the total force acting on that particular charge will be given as the vector sum of all the individual forces because of the other charges. So the total force on this charge Q1, let's suppose that's given by F, it will be nothing, it will be vector sum of F2, F3, and F4. F4. Or in general, if we have to find the total force acting on the charge Q1, if n number of charges are present, if n number of point charges, if n number of point charges are present, then net force acting on a charge, acting on a given charge is given by the superposition principle. That means that the net force on the charge will be given by F1 plus F2 plus F3 plus so on up to Fn. If four charges are placed in a space, then the number of forces acting on an individual charge will be 3. Right? If 5 charges are placed in a space, then the number of forces acting on the given charge will be 4. So in general, if n charges are placed in a space, then the number of individual forces acting on a given charge will be n minus 1. Let's try to solve some of the questions related to the superposition principle and try to find how the net force on charge q varies, or the charge q varies in the presence of any other charge. In this figure, we have three parts here. The question is, find net force on the charge placed at point B in the given arrangement if the side of each square is A. So in part first, here we have four charges placed on the corners of a square. We have four charges placed on the corners of a square. We have to find the charge on net force on the each charge because of the presence of other charges. Since all the four charges are positively charged, let's suppose we are trying to find the charge acting on charge Q, which is placed at point B. They are placed on a square. It means the side of each, the length of the each side will be A. The force on charge Q will be because of the charge A, charge D, and the charge C. And all the charges are positively charged, so all the charges will be repelling each other. The force on charge placed at B will be, because of C, will be in this direction. Let's call it force on B because of C. And the force on B because of charge placed at A will be in this direction. Force on charge B because of charge at A. And there will be third force, which will be because of charge placed at point D, and it will be along this direction. That's force on charge B because the charge placed at point D. Means the total force acting on this charge placed at B, that's net force acting on the charge placed at B, will be the vector sum of all the three forces. That will be FBC vector plus FBA vector plus FBD vector. For FBC, magnitude of FBC is nothing. It will be KQ square upon 4 pi epsilon naught A square. And similarly, the magnitude of FBA, it's going to be KQ square upon 4 pi epsilon naught A square. The magnitude of force on charge B because of charge at D, that's FBD, will be equal to KQ square upon 4 pi epsilon naught. Now the distance between the charge B and the charge D, it's nothing. This is the distance. And this distance will be nothing. It will be the under root of A square plus A square. That will be root 2A. Root 2A. So we'll be writing it here, root 2A ka whole square. So it will be KQ square upon 8 pi epsilon naught A square. So this will be the magnitudes of the three forces acting on the charge placed at B. We know the magnitude of the force because of charge C and the charge A are equal in magnitude. but they are placed at an angle of 90 degree. They are placed at an angle of 90 degree. So the total resultant of FBC vector plus FBA vector, and if I try to find the magnitude of these two forces, it will be nothing under root of FBC square plus FBA square. So it will be equal to under root of KQ square upon 4 pi epsilon naught A square plus KQ square upon 4 pi epsilon naught A square. So it will be nothing. It will be root 2 times. It will be root 2 times will be under root of 2 times KQ square upon 4 pi epsilon naught A square. A square. So from here 2 and 2 will go. So it will be left with KQ square upon 2 pi epsilon naught A square. So this will be the resultant of the two forces FBC and FBA. And this resultant will be along the force FBD here. This resultant of the two forces will be along the force FBD. So the total force will be the sum of resultant of FBA and FBC and the force acting on this charge because of charge placed at D. We can write here net force F is nothing under root of KQ square upon 2 pi epsilon naught A square plus KQ square upon 8 pi epsilon naught A square. So this will be finally the net force acting on the charge Q placed at point B, provided all the four charges are positively charged. Let's move on to the part 2 of this question. Now at point D, we have placed a negative charge, that's minus Q, and at point B also we have placed a minus Q charge. Now the system is like this. Charge here is minus Q and the charge here is minus Q. And here it is plus Q and here it is also a plus Q charge. Once again, they are placed on a square, corners of a square, and we want to find the force on B. The force on B because of charge C will be in this direction. Since minus Q and plus Q, they are the opposite charges, so it will be attractive force. It will be in this direction towards the charge C. Let me call this as F1. That's equal to minus KQ square upon 4 pi epsilon naught A square. Your minus direction here indicates that the force is attractive. So we'll not be taking care, we have already mentioned the direction of the force here, we'll be taking only the positive sign. It means that we'll be only taking the magnitude of this force. And similarly, minus Q once again will be attracted because of the charge placed at Q. It will be along this direction. Let me call this force 2. It will be once again KQ square upon 4 pi epsilon naught A square. And the force because of charge T, force because of the charge T, it will be, since at point T the charge once again is negatively charged, and at point B the charge is also negative, so it will be a repulsive force, so it will be along this direction. Let me call this as F3. The magnitude of F3 will be once again kq square upon 4 pi epsilon naught a square, and a is our root 2a, so it will be kq square upon 8 pi epsilon naught a square. The resultant of F1 and F2 force will be along this. It will be along the diagonal of this square like this. This is nothing, it's F1 plus F2 vector. And the magnitude of these two forces will be once again F1 plus F2 will be under root of kq square upon 4 pi epsilon naught a square whole square plus kq square upon 4 pi epsilon naught a square का whole square. So it will be root 2 times kq square upon 4 pi epsilon naught a square. So there is a slight correction in the previous question. In the previous solution, there will be a slight correction. It was whole square here. It's square here and here also. So the net force we'll be getting here is the net force here will be under root of root 2 times kq square upon 4 pi epsilon naught a square. We'll add here root 2 times kq square upon 4 pi epsilon naught a square. So this will be the correction here. So here the net force, because of F1 and F2, it's root 2 times the kq square upon 4 pi epsilon naught a square. But the force F3 is opposed to the resultant of F1 and F2. So the net force here will be given by, so the magnitude of the net force will be given by the vector subtraction of F3 and F1 plus F2. That will be kq square upon 8 pi epsilon naught a square root 2 kq square upon 4 pi epsilon naught a square. So this will be the net force on the charge Q placed at point B because of the rest of the charge. We can see the net resultant force acting on the charge P is different than the previous case because of the change in the sign of the charges. Initially, we were placing all the 4 charges for positively charged, but in the second case, the charge placed at point T and the point T and point P are negative charges. So the net force on the charge P will change now. Now there is third configuration given in this case, that now minus Q and minus Q charge are placed at point A and C. They are placed at point A and C respectively. Let's try to see what will happen here. In the third case, the negatively charged particles are now placed at these 2 points. Minus q is here and the minus q is here. And we have plus q here and plus q here. This is A, this is B, and this is C, and this is D. Once again, the charge placed at P will have a different force. Because of charge at C, it will be attractive force in this direction. Let me call this F1. And the magnitude of this force will be kq square upon 4 pi epsilon naught A square. And because of charge at A, it will be once again F2. It's going to be kq square upon 4 pi epsilon naught A square. And now the force, because of the charge D, it's once again the charge B is positively charged and the charge D is also positively charged. It will be a repulsive force along this direction. Let me call this F3. So it will be equal to kq square upon 8 pi epsilon naught A square. The resultant of the forces F1 and F2 will be along this. It's going to be under root 2 kq square upon 4 pi epsilon naught A square. The net force once again will be nothing. It will be the vector subtraction of these two forces. That's kq square upon 8 pi epsilon naught A square minus root 2 times kq square upon 4 pi epsilon naught A square. So this will be the net force here. This force will be dominating. This force will be dominating force here. The magnitude of this force will be dominating here. So that's how we use the superposition principle to calculate the force on single charge because of the presence of other charges. Now we have another question that AB is a right angle triangle in which AB is equal to 3 centimeter and BC equal to 4 centimeter. And angle ABC is equal to pi by 2. It's pi by 2 here. The three charges plus 15 electrostatic unit and plus 12 electrostatic unit and minus 20 electrostatic unit are placed respectively on A, B and C. The question is asking the force acting on charge B. The force acting on the charge B is, the situation is like this. Suppose that we have a right angle triangle like this. It is right angled at point B. It is right angled at point B. This is our A and this is our C. The three charges are placed like we have 15 ESU here. This is a positive charge, and at point B we have plus 12 ESU, that's electrostatic unit. This is a CGS unit of charge, and we have minus 20 electrostatic units of charge are placed respectively on A, B, and C. The question is the force acting on charge B is. The force acting on charge B is. Now there will be electrostatic force of attraction on charge B because of the charge placed at C, because both the charges are negatively charged. So the force will be in this direction. Let me call this force as F1. The magnitude of this force will be given by kq square upon 4 pi epsilon naught A square. Just a minute. So it will be q square upon 4 pi epsilon naught A square. Here in all the above cases, we have actually written the constant k here, but the constant k is actually itself 1 upon 4 pi epsilon naught. The constant K itself is 1 upon 4 pi epsilon naught. So try to omit this K here in all these situations because we have already written the constant K in all the cases. So we cannot write the constant K twice. Or we can say that the value of K here is 1. But we'll try to remove this. The force here will be Q square upon 4 pi epsilon naught A square. And we have been given the charge as minus 20 ESU and plus 12 ESU. So it will be 20 into 12 upon 4 pi epsilon naught A square. The value of side BC is given as this is equal to 4 centimeter and the side AB is given as 3 centimeter. So our side AC will be under root of 3 square plus 4 square. It will be nothing. It will be equal to 5 centimeter. So it will be 5 centimeter. Now the force on B because of the charge placed at A, it will be a repulsive force in this direction. That will be once again given by Q square upon 4 pi epsilon naught A square. And Q square, that's Q1, Q2, right? It will be Q1, Q2 upon 4 pi epsilon naught A square. Q1 is given as 12 and Q2 is given as 15 upon 4 pi epsilon naught A square. Now there will be, these are the two forces acting on the charge P because of the charge A and the charge C. The side A, here in this case, it's given as 4 centimeter. And here in this case, it's given as 3 centimeter. So the net force, because both the two forces are perpendicular to each other, so the magnitude of the net force between the two forces will be under root of F1 square plus F2 square, as the two forces are perpendicular to each other. So it will be under root of F1 square plus F2 square. From here we can substitute the value of F1, that's 20 to 12 upon 4 pi epsilon naught into A square, that's 16, and F2, that's equal to, in the second case the charge is 15, the second charge is 15, not 12, that's 12 into 15 upon 4 pi epsilon naught into 9, that's 3 square. So from here it will get cancelled by 4 and 3, so it will be 60, 60 upon 4, it will be 15. So F1 will be equal to 15 upon 4 pi epsilon naught. And F2 will be equal to 3 and 4, 3 and 5, 5 4 is 20, it will be 20 upon 4 pi epsilon naught. Now all these forces we have calculated here are in the units of CGS. They are in the CGS units. CGS units. If they are in the CGS unit, the unit of the force will be equal to dyne. So the unit of force will be dyne. We know epsilon naught has got value 8.85 into 10 to the power minus 12. That's the value of epsilon naught, but it is in SI units. And the value of 1 upon 4 pi epsilon naught, it's nothing in CGS units. It's equal to 1. That's in CGS. That's in CGS. We'll be substituting the value of 1 upon 4 pi epsilon naught as 1. So we'll be getting F1 equal to how much? 15 dynes. And F2 equal to 20 dynes. So our net force will be nothing. It will be under root of 15 square plus 20 square. So it's going to be 20 square is 400 and 15 square is 225. So it will be 625. 625. So it will be equal to 25. And the root of 625 is 25. So the net force acting on this charge placed at point P is nothing. The net force is equal to 25 dynes. So this is the net force acting on this charge placed at point P because of the other charge. So all these forces we have calculated using the concept of superposition principle. So what the superposition principle states is that if we have n number of individual charges, point charges placed in a space, the number one point is that the force between the two charges is not affected by the presence of any other third charge. And number two is that the net force acting on an individual charge or a given charge is the vector sum of all the individual forces acting on a given charge. That is, we have to find the force acting on a given charge because of the presence of all other charges, and then calculate the vector sum of all the forces. That will give us the total force acting on a given charge as well as the direction of that force. So that's how we use the superposition principle. That's how we use the superposition principle to calculate the force acting on different charges. And in the same manner, we'll be using the same superposition principle to see the equilibrium of two charges or equilibrium of n number of charges. By the using the concept of superposition principle, we'll be calculating the total force using the superposition principle, and then we'll be looking at the condition for the charge to be at equilibrium. All these things will be discussed in the next class, and that's it for today. And we'll be discussing the equilibrium situations in the next class, and we'll be taking up with the electric field lines. We'll be discussing the electric field lines, the properties of the electric field lines in the next class also, and some of the questions related to the superposition principle also. So till then, take care and goodbye.